Ladies and gentlemen, my name is Georg Ostermeyer. I'm the head of the Institute of Dynamics and Vibration in the University of Braunschweig in Germany. And it is great for me to be here again at the Asiabrake. Thank you for the opportunity to give a short overview on friction, wear, and emission of brakes in the real world. Especially wear and emission is a highly also political topic. Many research activities are to be found on these topics everywhere in the world. I will give a short overview on that, what we are doing in this field. Here you can see the content of my presentation. After some basics about friction brakes, I would like to go more intensively into wear and emissions. And a special prerequisite for that, however, are high precision measurement devices. Here I will only show some essential technical requirements for such measurements. Then, of course, I will show some new results on real-world wear and emission of brakes. I will conclude with an outlook. So let us start first with the basics of brake tribology. This is a basic layout of a disc brake. A brake pad is pressed against the disc, you can see it here, and in this process a boundary layer film is formed not only between the lining and the disc, but too on the entire friction track on the disc just here around. The topological surface structure of the pad shows a highly complex dynamical behavior. Friction in the microscopic world manifests itself as dissipation of energy and dissipation of material, that is wear. The underlying processes are almost unknown. And if you want to avoid ad hoc assumption, just like Coulomb's law or so, you have to go further and further down the scale of description to get more and more information until you are on an atomic scale. On this scale, however, there is no dissipation of energy anymore and no dissipation of material. Instead, there are energy distribution processes, material distribution processes, and of course, chemical reactions. So there is no dissipation anymore. In principle, you can describe these very precisely by quantum mechanics or quantum physics. But then, yes, you need about 10 to the power of 25 equations for 1 cubic centimeter of matter, and the time constants of the dynamics would be femtoseconds. You can't handle that for microscopic friction with these non-stationary molecular dynamics. So the question is, which of these many equations you have to delete to get the few essential equations for friction in the microscopic world? The main problem to describe friction is not the dissipation of energy, and it is not the dissipation of material, but it is the dissipation of information. But again, what of this huge amount of information on the atomic scale should be dissipated? Strange enough, nature itself provides perfect mechanism to dissipate information. One of these mechanisms is heat. Heat sums up all high-frequency atomic, molecular, and crystalline vibrations in a simple macroscopic scalar temperature field. Another mechanism is wear itself. Microscopic or even atomic surface details change at any time. But wear sums up all these geometrical microscopic changes and can be described with a few microscopic variables. With this in mind, a microscopic friction law should be at least a function of temperature and wear. Before I want to talk on friction laws, please let us have a closer look on brake friction. The simplest material structure of a lining is outlined here. You have sand grains, they're bound into a polymer matrix. Let's look at a small section of this lining which contains only, here you can see it, only a very small particle or one single sand particle. And if the grey cast iron now is pressed against it, a patch around the sand particle is formed, which can be seen in the REM picture on the right. Question is, how does this work? First, the polymer matrix is rubbed off the disk until the much harder stone particle, you can see it here, reaches the surface. This particle has a much greater wear resistance than the surrounding matrix. With the wear of the polymer matrix, the particle is pushed more and more into the matrix. In the sand particle, the normal force increases, and with it, the frictional force and the temperature. The high normal pressure between sand particle and rotor causes also wear on the rotor surface. This set of wear particles from the pad and from the rotor accumulate in front of the sand rotor contact and is compactified. Heat and chemistry causes melting and even alloying processes. Result is a tribal coating on the compactified particle set, so a rather hard patch is born which grows and carries by this more and more of the friction load. Of course, growing tribological load will cause the patch to develop something like heat cracks and limit the lifetime of the patch. At the end, the patch will be flushed out of the boundary layer, you can see it here. In special cases, this can be seen from the two maxima of the emission. They are the abrasion particles from the polymer matrix and the fragments of the patches. The surface of the pad is thus divided at least in two parts. Type 1, the soft polymer surface with nearly no dissipation, and type 2, the patches with a breathing total surface area which essentially co-determine the friction force. Birth and death of these patches can be seen as part of a cycle process I've sketched out here. The input power produces friction, and the friction produces heat and wear. The wear produces particles which, together with this heat, will form these patches. The wear itself limits the lifetime of the patches. Increasing the patch area causes an increase in friction power. Decreasing the number of patches causes a decrease in friction power. See these functions F1 and F2. This process, which has been greatly simplified here, can be seen as a closed loop that provides a simple time balance equation of friction. You can see such a balance equation on the right. This is a friction law of mine that describes mu dot as a function of heat and wear. If one discretizes the boundary layer and feeds it locally with the geometry, the materials, and local thermodynamic processes, one obtains a patch dynamic and temperature distribution is found in the real break. You see here the animations on the left. This patch dynamic is a very stable self-organization effect we found in many other tribal contexts too, for instance, on artificial hip joint shells or on railroad tracks where these patches appear as a wide, hard layer, at least causing the periodic ripples in the rail wheel contact you have surely heard about. To investigate the usefulness of the friction law for brakes, we can consider, for instance, the calculation of NVH stability with complex eigenvalue analysis for a given simulation model. One of the new scientific drivers of describing not fully understand physical processes is the uncertainty analysis. And we consider by this the differences of the friction laws to the measurements as uncertainty. And we use Coulomb's law on one hand and the balanced friction law I've just shown on the other slide just to describe this process. You can see the result here. For details, please see my paper from 2019. You see the cumulative distribution function over the maximal real part of eigenvalues. The underlying measurement data set contains more than 50 million data points. Blue is the uncertainty range regarding the prediction of NVH with Coulomb's law, optimally matched with the measured data of friction. More than 20 times more accurate is a prediction when using my second-order friction law, see the red area. The friction law can of course be improved, but already this first version of the friction law, which is already more than 20 years old, allows much more detailed analysis in real-world NVH than Coulomb do. The key is the a priori knowledge on brake friction on its dynamics. Now I would like to briefly discuss measuring devices for wear and emissions. There are, of course, very many devices and instruments in industry and research. I will concentrate on a few measurement devices, and I would like to explain here why I use this particular selection of devices. Here you can see the wide range of possible measuring devices that is in use, from the complete vehicle on the real road to the pin on disc tester at the bottom right. If you test and measure a complete brake, then you must take into account that the pressure, temperature, friction conditions over the brake lining vary very strongly in time and place during a brake application. However, wear and the generation of emission particles depend very much on these variables. So if you study an entire brake in, say, a dynamometer, you are integrating across very different states in the pad, which makes it very difficult to analyze dependencies. A pin-on-disc tester can be used to investigate a small section of a real lining where much more controllable states can be set in the tribal contact. Here you can see a rough sketch of our fully automated tribal tester. The pin 2 to 4 square centimeter pad cutout is guided over a high precision XY table to the brake disc and to many other instruments, for instance cameras, surface scanners. Not shown here, the Y table runs on the outer side on an additional rail to catch moments from the friction force of the disc. The device measures, among other things, the forces, the speeds, the temperatures at disc and lining, and calculates immediately the friction value with approximately 10 kHz. In addition, of course, weather data, noise, and vibrations are detected. We actively use data science technique for compression and evaluation. We can run fully automated, complex brake application. We can compress the surface scans to movies. Here you can see the loading unit. It has the pin and the holder. It is an elastic joint with only 1 degree of freedom, which presses the specimen onto the brake disc with adjustable elastic force. Even though this device is very stiff outside the one elastic direction, small deformations of the pin holder can occur, which are enormously damaging information, especially by wear and emission measurements. This is what I have illustrated here. If, for example, the mu value changes, and it does so always in the brake and wheel operation, then the changing frictional force causes a deformation of the pin holder or a change of the deformation of the pin holder, and thus also a tilting of the lining sample with respect to the rotor. This leads to a reduced contact area over a longer period of time with significantly higher energy densities inside this contact area. Interestingly, this has nearly no effect on the coefficient of friction we are measuring. This is consistent with Coulomb's idea, but it has a huge impact on emissions since the underlying processes change dramatically as a function of energy densities as we know now. The solution is an adaptive device which adjusts the pin so that it always is in full contact with the disc. The principle is shown here on the right. The motor lifts the rear spring assembly just so that it fits perfect to the disc. We knew the actual friction force and the elastic properties of the pin holder. With that, we can compute the tilting area, which is then compensated by the motor on the right side. Here you can see this device in operation. At the top of the round rectangle, you can see a flag on the shaft of the motor that provides adjustment of the pin. You can see that it works continuously with the transient braking. This is absolutely necessary as it is the only way to get accurate wear but also accurate emission values from the sample. In addition, this device also has complex hardware-in-the-loop control mechanisms. If you give us real speed or driving profile, you see it here on the left side, we can accurately track that with the associated brake and vehicle data. In doing so, the associated brake pressure is automatically determined based on the real-time availability of the friction rate. In addition to wear, emissions will also be measured by us. Of course, we have a range of precision measuring instruments from TSI and Pallas, you see it here on the left, which are particularly, of course, very useful for accurate validation of measurements. Early on, we focused on cost-effective alternative. On the right, you see a commercially available particle counter. This sensor costs only about $20. Some features are listed below. But what can you do with this sensor? We measured on our tribometer with a Pallas instrument and the low-cost sensor in the lab at the same place. Here you see the result for about 150 brake applications with very different operation modes. Red, the results of Pallas; blue, the results of the plane tower sensor. You see a shift in the measurement data. Obviously, we have to calibrate each plane tower sensor separately. But nevertheless, both instruments see the same events and nearly the same shape, even on very short timescales. Note that the Pallas instrument costs more than $40,000, whereas the plane tower sensor is about $20. After calibration, the results look very good even for single brake events. The difference over time are very small. Note that these measurements were not performed in clinical clean rooms, but without special preparations in my laboratory, with all the fluctuations usually there, which explain these deviations very well. Of course, you need some electronics to really use the plane tower sensor. Here, my institute has built up an own development. We use SMD techniques, and we have a special small microcontroller for this. We have automatic sensor recognition. Please think of that. There are about 20 of these sensors to be found in the market. We have a power bank with an operation time of 10 hours with an intelligent charging structure. We are measuring the temperature, humidity, the GPS signal, and all the data 10 hours, 1 hertz, are cached on a memory card. Of course, we have Bluetooth, and the sensor card can even build up ad hoc networks. This is a starting point for us to go into the swarm sensor technology, which we want to use for the real-world emission measurements. That means many rather cheap sensors are used to get a dense field of information on emissions in time and space. Now we come to some measurement results. The literature often talks about friction and wear, without saying what kind of timescale the authors are talking about. But this is essential, as I would like to show here. Here you can see the wear over long timescales. That means more than 1,000 brake procedures. Plotted is the amount of wear over the idle work. The idle work is a normal load times the friction weight. On this timescale, wear is practically linear. This corresponds to the classical Archard's idea. So Archard's law for wear prediction is rather good for most of pads when looking on the total lifetime of a pad. But even on an average timescale, which is about 200 or 250 braking operation, significant deviations become apparent. The amount of wear can depend directly on the speed or also on the braking dynamics. On the left, you can see clear differences between steady state, and transient braking operations. This is not to be found by any friction pairing, but contains a lot of optimizing potential when looking on meaningful brake operations with minimal emissions. This becomes even clearer on a very short time scale. Here, the mean altitude can even increase, again due to the braking operation. This effect is sketched here on the left side, and I called it reservoir dynamics. One finds that certain braking conditions collect the wear dust in the boundary layer, especially in the holes on the boundary you see here. Other braking activities show the brake dust in the boundary layer out again. Emissions are usually considered on this timescale. Emissions are not proportional to the wear processes there. Therefore, it is not only the current wear that is important, but also the load history. This has a significant influence on the coefficient of friction, wear, and the emission dynamics on a short time scale. Been the focus of research for several years. I gave a detailed presentation on this at Asiabrake in 2018. What is so special about brake emissions? Aerosol dynamics play a key role here. You can see the emission modes plotted against the particle size on this axis here. From the left, gases like NOx and VOx, that nitrogen oxides or volatile organic compounds, form aerosol particles moving to the middle of this diagram through nucleation, condensation, and coagulation. From the right, abrasion, erosion, and milling processes can cause a stream of particles coming to in the middle of this diagram. The middle part of the diagram just marks a size range with very stable and long-living particles in our atmosphere. Brakes emit particles exactly in the middle of this window. Measurements on the described tripod tester allows very detailed statements about the flow dynamics of brake particles and equally precise analysis of the influencing parameters. We have shown this with complex CFD DAM simulations in 2021. My vision is that not only friction itself, but also wear and emission can be described by a differential balance equation, as I've shown them just at the beginning of this talk. In addition to heat and wear, reservoir dynamics also play an important role. With recent results on milling and chemotribology, I've just got very nice research projects for the next years on it. We hope to be able to predict emissions dynamically. One goal is to characterize the emission behavior of a vehicle as a function of its driving dynamic. Here you can see how something like this can be measured. We have set up a number of sensors sparkly next to the road and analyze emission during braking actions of the vehicle. A first step to the analysis of the swarm sensors you can see here on this video. This first step uses only linear interpolation techniques. Once again, the cars are running here through, and in front of these sensors, these yellow boxes, they do braking actions. If you look at a single braking action, you can already make initial statements about the emission dynamics. An emission cloud forms, not higher than 2 meters, which sinks to the ground again after a short time. Of course, many weather influences also play a role here. Much more clearer are measurements at the car itself. We mounted our sensors at a lot of cars. Data science gives us possibilities to analyze principal emission properties of cars. This will be published soon. Our long-term goal is a complex city simulation. Here you can see the movement of the air in the city as the wind blows from the top to the bottom of the image. Of course, this is not just a nearly two-dimensional event, but the air caps upwards play a significant role. On the right, you see, for instance, a current picture of the Tonga volcano. Clearly, you see different layers in the high where the smoke changes its size totally. So we use our sensors not only in the city, but too in quadrocopters, analyzing the vertical properties in the city. Please let me conclude. Friction alone is a very complex dynamical process, as I have shown at the beginning of this talk. You can describe it, for instance, with differential balance equation. But friction, wear, and emissions are interrelated in a similar, very complex way too. I think there will be a good chance to describe wear and emissions with additional balance equations. Another point I wanted to come into the focus by this talk is it is essential that you always explain very precisely which size and timescale you are making statements about this. That is not always the case in the literature. And it is very important to understand what brake emissions actually do in nature. Of course, there is a healthy aspect of these emissions, very essential. But even actual is how do the particles change on the way from the brake to the environmental world? And where are they deposited and stored? On the street and re-pushed when the next car runs through, in groundwater or in plants? These are all open questions. Maybe the next time I can tell much more on these topics. Thank you for your attention, and I'm now open for any questions. Thank you.